In this video we're going to look at atomic structure, in particularly electron configurations. We're going to be looking at how the model that we have learnt in previous years doesn't work anymore, to explain what we need to know, and how we can use a more stringent model to explain properties of atoms, particularly the transition metals, but also so we can do the electron configurations of the first 36. So our traditional model, or Bohr model, that we have always been taught at school, has basically had this overview. If we have a look at sodium, which has got the atomic number of 11, that means that it's got 11 protons, and because atoms are neutral, 11 electrons. We would have arranged these in this way: the 11 protons and the neutrons, but we've ignored these, in a very small nucleus, and then orbiting that like planets around the sun, we'd have the electrons arranged in shells or energy levels, 2 in the first energy level, 8 in the next, and then up to 8 in the last one. This would give us an electron configuration of 281 for, in this case, sodium. That explained why sodium easily became an ion, sodium plus. It had 1 electron in its highest energy level, and that was easily lost. So this model worked pretty well for the first 20 elements. It explained what ions they became, or if they didn't become ions, what their valency was for sharing electrons. However, what we now know is that it falls down beyond number 20. And instead what we've found is that those energy levels are still right, 1, 2, 3, 4, like we had for our first 20 elements, but the way that the electrons are arranged in those energy levels is quite different. They're arranged into little things called orbitals. Now, to put it simply, I hope, an orbital is basically a space around the around the nucleus, where the electrons spend about 95% of their time. They don't spend all their time there. They don't go in lovely elliptical or spherical or circular orbits. They go in quite random directions, but they spend a lot of their time, over 90% of their time, in this particular orbital or area. In the first energy level, there's only one type or one shape of orbital, and that's the s orbital. These are basically a spherical orbital, and they can take a maximum of 2 electrons. So therefore we're saying that the first energy level can take up to 2 electrons. Just like in our Bohr model, we said that the first energy level, or first shell, could take 2. Then we find that electrons with a higher energy level can be found a bit further away from the nucleus. And they can be found in 2 different shaped orbitals. One is the s orbital, which again contains our 2 electrons, which we can see here. And then there's a group of orbitals called the p orbitals, and these are sort of a dumbbell shape. Remember, this is not the orbit of the electrons, it's just where they're actually found for most of the time. And we find that there are 3 sub-orbitals, or 3 dumbbell shapes, each of them able to take 2 electrons, so your p orbital can take up to 6 electrons. So 2 plus 6 is 8 in our second energy level. This is all sounding very, very similar to our Bohr model. And until we get up to number 20, things keep staying the same. We've got S and P at 3, which will get us to 2, 8, 8. And then after we've filled the p orbital, the next 2 go into the fourth energy level, into its s orbital. So that's like the calcium 2882 would be 1 for the energy level, S2, it's got 2 electrons there, 2S2, 2P6, 3S2, 3P6, 4S2. So if you play that slowly again, that's 2, 8, 8, 2. However, if we go to scandium, things get a bit different. Its electrons are not at the fourth energy level. They're at a slightly lower energy level, actually a considerably lower energy level. And they're actually put in the third energy level. And these have a different orbit again, or a different orbital I should say. And they're called the d orbital, this one here. And there are 5 suborbitals that make up the d orbital. So therefore another 10 can go in there. And that makes sense. If we look at the periodic table, the transition metals, so that's from scandium to zinc in the fourth period, there's 10 of them. So that makes sense that you're going to be adding one electron to the suborbitals as we go along. This doesn't really make a lot of sense until we put it into practice. So I'm just going to go through a couple of transition metals and their ions actually and look at their electron configurations the way that we should be writing them now using this quantum mechanics model. Just a reminder that rather than shells, we're now looking at energy levels, and that these energy levels are made up of orbitals, which is where those electrons spend most of their time. The s orbital contains 2 electrons, up to 2 electrons. The p is made up of 3 suborbitals, so it can take 6 in total. And the d orbital is made up of 5 suborbitals, so it can take 10 electrons. Just a quick note that I forgot to mention, the s orbital fills before the p, and the suborbitals fill before you start pairing the electrons up. So when you've got 1 in each, so the half-filled suborbitals, so P3, then what we see there is what we call maximum spin. All of them are spinning in the same direction. And these arrows are representing electrons. Okay, what does this actually look like? Well, here I've gone with scandium first of all. And we've got the 1s electrons, and there's 2 of them, so we write that as 1s2. I've got the 2s electrons, so we write that as 2s2. And then I fill up the p orbital, so 1s2, 2s2, 2p6. This one here's the third energy level, so 3s2, 3p6. Then I go to the 4s, just as if I was going to calcium, so 4s2. But scandium's number 21, so where do I put that other electron? I put it into the 3d orbital. If you add up all these little numbers, not the big ones, the little ones, that should add up to 21. Now, that's a pretty disorganized way to write it, so this is how we normally write it, in either of these ways here. The top one is listing out every single one, and it's really easy to make a mistake. Whereas the bottom one goes to the nearest complete energy level, or noble gas. We put the the symbol for the noble gas in square brackets, and then we carry on with the rest of it. So you'll see 1s2, 2s2, 2p6, 3s2, 3p6 is the electron configuration of argon. So then I've just copied that there. Much easier, and it's more likely you get it right. So scandium looks pretty easy. We've just done the same electron configuration as calcium, then put 3d1 at the end of it. What it's worth noting is that scandium makes a 2+ ion, and so actually the 4s electrons are lost first, and that's because they're a higher energy level. It takes less energy to remove these electrons than it does to remove this one. Okay, let's have a look at some that aren't quite so easy. First of all is copper. Now you'd expect copper to be the argon configuration, then 4s2, 3d9, but actually we find that it's argon, then 4s1, 3d10. The reason for that is that when it's the second one, you have a complete orbital. Actually, the third energy level is completely full. This is a much more stable arrangement, so this is what ends up happening. It's a more stable arrangement, so that's the electron configuration. Another one that's similar to this is chromium. For the same sort of reason, we see that instead of being 4s2, 3d4, it's 4s1, 3d5. You'll see that all the electrons in this one are shown as upwards arrows. That means they're all spinning in the same direction. This means we have what's called maximum spin. A half-filled orbital is more stable than one that's got, say, 4 electrons in the orbital, so for d orbital. So that's a lot more stable than the alternative arrangement. And this one's called Hund's law, or Hund's rule I should say, where this is the more stable arrangement because it's got maximum spin, or half-filled orbital. Okay, so what about making ions? Let's have a look first of all at copper, because copper makes 2 different ions. And the first one actually seems to make more sense than the second one, even though we all know that the more easily or more readily made ion of copper is actually 2+. Copper sulfate is CuSO4. Copper is argon, then 4s1, 3d10. Again, 3d10 because this is full, and that's not a lot less stable than 4s2. So to become the copper plus ion, it loses the 4s1 electron to become 3d10. Now you don't need to know why that is less stable than the Cu2 plus ion, but for some reason it is. But we can see quite easily why it becomes this ion. It loses its fourth energy level electron, and you'd expect it to be very, very stable. To become copper 2 plus, we see that now it's gone to 3d9. So it's lost the 4s electron, then it's lost the 3d electron. So the reason why this is a stable arrangement you don't need to know. That's not assessed. Let's look at manganese. It does the same sort of thing. Manganese is number 20. Sorry, just got to remember quickly. 25. And so that's argon, 4s2, 3d5. Again, it's quite obvious to see why manganese makes a 2 plus ion. It just loses the 2 electrons that are at the highest energy level to become argon 3d5. Now you could argue that it would then lose those 5 electrons to become manganese 7, but as we know from learning about the Bohr model, to lose that many electrons takes too much change in energy, so it doesn't happen. However, manganese 7 does exist, but it's not an ion. It's an oxidation state, so it's involved in bonding with other elements. So its electron configuration, which we'll go back up to here, is a bit of a giveaway as to why that could exist. So there we go. There's a quick overview of the electron configurations and what you need to do with it. Just a reminder, you need to be able to write the electron configurations for the first 36 elements, and you need to write the electron configurations for their ions if you're told what they are. For example, you don't need to know that iron becomes Fe2 plus and Fe3 plus, but if asked, you should be able to write the electron configuration for Fe2 plus and for Fe3 plus.